Howdy, folks. Welcome back to CS128-Honors. I hope you had a wonderful weekend, and today we're going to be discussing ownership examples. And today's lecture is going to be a little bit different in structure, rather than being mostly conceptual with, well, I don't want to say little code references. Today's lecture is going to be, or lesson is going to be almost exclusively exploring code, walking through code together. So let us know if you like this sort of structure, if you think that this is helpful, if you think that it's not helpful, if you want to see it in a different way, whatever. Additionally, apologies if this video comes out a little bit late. I've been gone since Wednesday last week, and so I'm only getting to this now. So hopefully this should still come out before midnight, but if it comes out a couple hours later than normal, I apologize. So let's get started. So just the main stuff for today is to go over ownership concepts, and more specifically the examples that we'll see with the concepts, putting them into practice, stuff like borrowing, stuff like, using the references, ownership in general, scopes, stuff like that. And we're going to pull heavily from the Rust by Example GitHub. It's really awesome. We'll use, actually, that's where kind of all of these examples are coming from. It's a great resource. I encourage you all to use it yourself if you're ever curious. However, I'll walk you through some examples about borrowing and references now. So I guess no need to use those. Don't forget, MP1 is now out. It's due Wednesday, October 6th, so about 2 weeks from now. Y'all should have plenty of time, or I guess it's a little less than 2 weeks now since it was released last Wednesday, but y'all should have plenty of time. Again, make sure you're making the most out of office hours. And if you have any questions, just let us know. One thing I will mention is this MP is a little bit longer than MP0, so I do encourage you to get started as soon as possible. If you're hearing this, it's probably Monday or Tuesday or Wednesday of this week of the 27th of September, and so I encourage you to get a little bit done this week if you can, maybe pass some of the test cases. It'll help you a lot. You'll thank yourself next week. Okay, so major rules of ownership. So each value in Rust has a variable called its owner. There can only ever be one owner, and when an owner goes out of scope, the value is dropped or deallocated, deleted, whatever you want to call it. Additionally, with Matt, you learned about referencing and borrowing. You can have many immutable references or one mutable reference. So I want you all to keep these rules in mind as we're looking at these examples, but let's go ahead and dive right into examples. Okay. So if y'all are curious, this is the Rust Playground. It's an online sort of compiler and executor for Rust. I encourage you to use this yourself. If you don't want to develop locally, for which I highly recommend for larger projects like the MPs, but for homeworks and maybe smaller tasks, just seeing if something works, like if a line is valid and it works how you expect it to, the online Rust Playground is a wonderful, wonderful tool. Okay, so let's explore what we have here. So first we have this function called destroy box, which takes in a box, and basically it does nothing with it and destroys it, right? I mean, if you remember from Matt's lecture, this is because this function will take ownership of this box. Whoops. And then the function goes out of scope, thus the box goes out of scope and the box is dropped. Then we have our main function, nothing too crazy here. We allocate an integer, we copy y into x, we print the values, we allocate a box object, we print information about the box, we allocate b into a, we print information about a, we destroy b, we print information about b. So let's explore basically what's happening here. So hopefully y'all remember, let me see if I can pull up the drawing tool. Hopefully it's still set up. Give it one moment. Give it an extra moment. Okay, let's see if this works. Nope. Okay, I can actually fix this. I just need to swap this over. Okay, now it should work. Wonderful. Okay. Let me make it a little bit smaller. Okay, so first here we have we're initializing some variable on the stack. And if you remember what Matt said and what I said, you might remember in this case, the ideas of kind of borrowing and ownership don't as much apply, because with scalar values that have kind of static values and they're on the stack, we have the value x here. When we create a new local variable, we actually copy that value over. So we'll copy 5 here, and this is y if you're curious. And of course, then we're going to print the two statements. with this println. Looks a little bit strange on my screen. I hope that that's going through all right. Let me make this larger. Okay, yeah, y'all can see it fine. You know, nothing kind of crazy happens here. We're able to kind of copy the values of x into here and y into here. And this line does kind of perform as intended. So nothing too crazy there. We can use both values easily, right? Big idea here is this ownership doesn't really apply in this situation. However, now we're allocating something on the heap. A is on the heap. So I'll draw the heap here. And we have some space that holds A. Okay? And in fact, when we print A, we can contain information, or we can still print easily information about A. However, now when we say let B equal A, if you remember what's happening on the stack, A is only kind of information about the box, right? Most notably is the pointer. And that's going to point towards the location where the data is actually held. And so when we say let B equal A, what's actually occurring here? If you remember from my lecture lesson last Monday, we don't copy the data from A. We don't necessarily copy the pointer value from A. What we do instead is transfer. We move the pointer value into B. So now only B contains the pointer data. And so, for example, if we were to print this line, would this line work? Would we get an error in this line? And I'll give you a moment to think about it. So no, of course it wouldn't, right? We no longer own this data. A is kind of no longer owns any valid data. And so if we're trying to print the value of A, or the data contained in A, we won't get anything, right? Now let's build on this. We do know that B has the valid data now, and so we pass it into the destroy box function. And the destroy box function takes ownership and then leaves scope. And so now the question is, if we try to print B, will we get anything? And maybe you know the answer, maybe you don't. I encourage you to maybe pause and think about it for a moment. And of course we wouldn't. So at this point, if we run, we can see that our code will execute and compile. We see x is 5, y is 5, so that's from up here, completely normal. We let A contains this box just contains the value 5. We'll print out that value, and we can see that that is in fact what it contains. And then eventually when we call destroy box right here, we'll say it's destroying a box that contains 5. Now, if we were to say uncomment this line, we would see an error that says, hey, you're trying to reference a value that is already borrowed. And of course, the Rust compiler gives us very useful errors. It says, hey, this is the line that you actually moved the value. This is where you're trying to use it. All that super helpful stuff. Additionally, if we attempted to do it here, what's it going to say? Of course, it'll say, hey, this value is already destroyed. You can't use it. Once again, it'll say, hey, you've moved this value into ownership of this destroy box function, which, technically we're calling C, but hopefully, even if I called this B, the same thing here, it wouldn't cause any additional confusion because, they are different variables, right? Different scopes, confusion. Okay, and so once again, we get an error there. So hopefully, these examples are going to get more complex as we go, but hopefully that one's a little straightforward. Let's look at our next example now. Okay, so we have some box that we put the number 5 into, and this box is immutable, right? We don't have mute here. And we will print the value of the box, and this occurs normally, nothing too surprising in this situation. And so now what we'll do is we'll say let mutable box equal immutable box. So we are moving, well, actually I encourage you to imagine here what happens. So does this line work is my question essentially. And the answer is actually yes. So some of you might think, no, you can't make something mutable if it is immutable, but you can because we're actually moving the value into a new owner. And that new owner is mutable, right? So we move the box, we're changing the ownership and the mutability of that object, of that data on the heap. And we can print what the box contains. Then we dereference the box, and we change the value. We change the data within the box to be 4, and we print that value. Is this allowed? Of course it is, because we now have it be mutable. Now, I would ask you the question, is this allowed? So technically in this situation, the kind of question becomes, we are not necessarily changing a mutable box. A mutable box is a pointer, and that pointer is remaining in the same location to, some box that contains the value 5. If we change the value 5, is that still changing what we call a mutable box? And of course, hopefully this isn't too surprising. That does count as changing it. So it does not compile. You cannot assign a new value to an immutable object. However, when we remove that line once again and we compile, we can see that this performs exactly sort of how we expect. We're able to change the value here. And the box, we've changed the mutability of the box as well as the ownership of the box. Additionally, I might ask you for fun, what happens here? And so let's run it and we'll explore. And of course, we're going to get an error. And why is that? It's because we've moved the value, right? Even though we've changed the mutability, it's still a move. We still lose the data within a mutable box. This no longer owns this data, and so we're unable to sort of read from it. And once again, I got one question that I'll just touch on very briefly, which is, why do we have all of these rules? And the heart of it all is Rust is built to work in a multi-threaded fashion, to have multiple threads, processes, working on the same program at the same time, which I could talk about for a very long time on why that's sort of very beneficial and a critical paradigm of programming and good software development in the future. But instead of going into that right now, I'll hold off for when we're actually discussing parallelism. And instead, I'll just give you the idea. If you have two threads, we'll say a little CPU core here and a CPU core here, that are both trying to read information from some data in memory at the same time. Nothing bad happens if they're both reading. But if one of them begins to write, or maybe even worse, both of them begin to write, or read and write, either one, really funky things can happen here. And it's what we call race conditions, which is if on the same clock cycle, this CPU tries to say like X, say dereference X equals, X plus 1, and this CPU tries to say X is equal to, 2 times X or something, right? One of these is going to get there first. And so either the final value of X is basically going to be 2X plus 2, or it'll be 2X plus 1. And of course, there's no reason why one is more or less valid than another. And so that's what we have to worry about when we do this. And this prevents that from happening. Because in that situation, we would have two things writing to the same data, which would mean that we would have two mutable references to the same data. And of course, that's not allowed. Great. Let's move on to the next example. Okay, so this one's a little bit longer, but let's walk through it together. We have some function that destroys a box. Once again, takes ownership of the box, leaves scope, destroying the box. We have an additional function that borrows just an integer in 32. And so now we'll have our main function. We'll create a new box that has a 5 in it. We'll create an int 32 on the stack that has the value 6. And we'll borrow both of these values. And of course, look, once again, this borrow function is going to print it. So first of all, I should ask you, at this point, does everything sort of, I'll say, work as intended? And of course, there's no reason why it wouldn't work as intended. Borrowing is a function of the Rust language, and we've done something sort of more basic here. And so I hope you all understand that like everything above this point is completely valid. So now we're going to enter a new scope. Okay, and that's what these curly brackets are denoting. It's just there's some new scope we're entering. And we're going to have a new reference, and it's going to be a reference to the box, okay? And then we're going to pass, or first we will destroy the box, okay? And then we will attempt to borrow the reference to the int. Okay, so let's break down what's happening here. So we have some box that has the value 6 in it on the heap. Denote this with an H. And then down here, we have a 5. And this is on the stack. I'll denote this with an S. Even though my S's and 5s look very similar, I encourage you to realize they're somehow not the same. Wow, they really look similar. The 5 actually looks more like an S. That's, oh well. I hope you all understand. And so what we're doing here is we're borrowing these values in this first function, we're printing them, and we're returning that borrow, right? We're kind of getting rid of that immutable borrow. And so nothing bad happens. That occurs normally. Now we enter some new scope. We attach a reference to this. And of course, we already have our sort of, I'll say, original reference, even though it's not as much a reference as it is the owner. And then we transfer ownership of this into the eat function, and it destroys this, and it drops this data. So my question to you now is this valid? Is having this extra reference to some dropped data valid? Will the Rust compiler catch it? Do you need to worry about this? And of course it is not valid, and the Rust compiler will catch it. And because you now have this pointer to unallocated data, which not only is going to lead to unintended behavior, but can also be a very significant security flaw. If you say allocate a very large portion of data and then deallocate that data, yet still have the permission to read from that data, other programs might allocate information in that space, and you would be able to read information from other programs from your program, which could be very serious if you were able to deduce what it is you're reading, which is maybe less difficult than it seems. So of course we can comment out this line. Instead of destroying this data, we'll just we'll borrow a reference to this and we'll run it, and everything acts normally. And once again, just to break down what's happening here, at this situation, we're borrowing a reference to the int. And then this borrowed reference goes out of scope. And now we can destroy this normally, because this borrowed reference is now out of scope. So, and I'll give you all a little bit of a trick question here. Do you think that this will compile? Having this, this won't compile because we eat it twice. But in this situation, will it compile? And the answer is yes. And I want you all to think for a moment why. And the answer maybe is not as easy as it seems, or maybe it's not as hard. It's just kind of strange. So in this situation, the Rust compiler knows is the answer. It knows that we're no longer using this reference to int32. And so it knows at this point, on line 28 basically, it can now drop ref to i32. And so we will lose this reference, and we're able to freely drop the box without worrying about it, right? Because the compiler knows this data will no longer be needed in the future, and so it will insert this sort of right here. Of course, this happens naturally in this situation, because when we leave the scope, it is automatically dropped. So in this situation, the drop is really occurring, not that it makes a huge difference, right here. So just a little interesting tidbit. Sometimes the Rust compiler can really save you like that. Okay, let's move on. How much time are we at? Let's check. Okay, 18 minutes. This might be the last one. If I can get through 2 more, I will, but we'll see. I'll speed it up a little bit, maybe. Okay, so in this next example, we have, actually, we'll probably be fine. Okay, so this is an example that we use structs in. Structs are just ways of sort of organizing our data together. And so what we have is an author that is a reference to a static string. Note that this is not string, which is on the heap. Title is a reference to another static string, and the year is an unsigned 32-bit integer. We have the borrow book function, which immutably borrows a book. We have the new edition, which mutably borrows a reference to a book. I should mention that this one's also a reference. That mutably borrows a reference to a book, changes the year, and then prints that it did that. And so let's explore some. So first we're going to create an immutable book called immutabook. Once again, these string literals, we can kind of pass directly in since they'll have that correct type. And we'll give it the year 1979. And we'll create a mutable copy of this book. So first question, is this valid? And of course it would be valid, right? We're creating a immutable copy of the book. And the kind of an important thing to notice is all of this is on the stack. And so we are able to kind of copy this book normally. This is not necessarily on the heap, even though it is sort of a, I'll say object, which might be bad terminology to use here, but oh well. So now we'll create a mutable copy of that book. And so if we borrow a reference to the immutable book, is this valid? So we pass a reference to an immutable book. We have one immutable reference. We print information about that. Of course, that is valid. Can we have an immutable reference to a mutable book? So we have a mutable book. We take an immutable reference to it, and we print information about it. Of course, that is still valid. Now let's have a mutable reference to a mutable book. Is this valid? So some of you might say no, because the book is mutable, but this book is not a reference. And so we are able to have one mutable reference. And so this is valid. Now, can we take a mutable reference to an immutable object? And hopefully with this, y'all can understand that no, that's not allowed. This is an immutable object, and so we're not allowed to take a mutable borrow with it. I feel like the word, you ever say a word too many times and it doesn't sound like a real word anymore? Mutable is now not a real word to me. Gosh, it's even hard to say it. Should have had water. Okay, and we can see that this performs as expected. We even mutably borrow this mutable book and print the new information about that book. I might also ask y'all, if we put, for example, this print statement here and printed the mutable title and mutable year, what would we get? Of course, we've passed in a mutable reference. That's the whole point of mutable references, is that they are going to actually change the information. So it would change it. Okay, wonderful. Last example, and we should still be good on time. There's one more example after this, but I think it's sort of a strange edge case that y'all don't necessarily need to know about, but I'll maybe briefly mention it if you do feel like exploring it yourself. Okay, so we have a point, struct tuple, just stores three 32-bit integers. We initialize some struct tuple with the points 0, 0, 0. Of course, the points here probably don't really matter. And we're going to take borrow two immutable references to this mutable object, or mutable struct, I should say. Okay, and for the first print statement, we'll print out the word mutable really doesn't sound real anymore. For the first print statement, we will simply print the x, y, and z, taking kind of one piece from each of them. And is there any reason why this should be invalid? Absolutely not, right? We can kind of print whatever we'd like there. They could be totally different things. It doesn't matter. Now, I'm going to ask you all, if we have here, let mutable borrow equal a mutable reference to a point, is this valid? And of course the answer is no. You can't have immutable references as well as a mutable reference to the same thing. But once again, I'll throw this kind of edge case in. Is this valid now? And the answer would technically be yes, because the compiler knows that at no point after this you're going to use borrowed point or another borrow. But it will also mention that you aren't actually using those things. Well, neither are you using this, but okay, let's put that code back. Let's compile, and we'll see that it now errors out. So we can see immutable borrow occurs here, and we have immutable borrow and then immutable borrow after that. So, obviously that will not compile. Okay. So obviously this value is used. We have this to prove that these values will still be used afterwards, so that the mutable borrow would not be valid. I'll put it back just for reference. Okay, and so now at this point, let's now take another mutable borrow, but we're going to do it in such a way that we aren't necessarily using the same data later. Or at least we'll explore that as we go. So we're going to take a mutable borrow to this point, and we're going to change the values of the mutable borrow. So we'll change x to 5, y to 2, and z to 1. Okay, so my first question to you all is, if we uncomment this line, is this valid? And I will mention that we are not using another point and another borrow, or borrowed point and another borrow after this point, so you don't have to worry about it erroring out, previously. So actually, in fact, I can compile and show you. And we can see that it does run, but I won't let you, I won't spoil it, what happens already. Okay, so is this valid? And of course the answer is no. We have a mutable borrow already, and so we cannot take an immutable borrow. And we'll run it just to check. And we can see it does not compile. Mutable borrow later used here. Immutable borrow occurs here. Great. Okay. Additionally, can we do this? Is this valid? And so we'll run it. And this is in a little bit of an interesting case, but it's actually not valid. And that's because println takes an immutable reference. And we can't take an immutable reference if we already have something that is mutable. And once again here, the idea is the same, right? If one thread is attempting to print this value, while another thread is attempting to change that value, who knows what the correct thing to print is? After the person or after the other thread changes it, or before? So there's really no answer. And maybe that's insight into why that doesn't work. Whoops. Okay, now we can print out the coordinates of this point. Remembering it's an immutable borrow, we expect 521. And then we can take a mutable borrow to the point. And since we no longer use mutable borrow, we can see that we had this mutable borrow, we changed the data, and we do in fact see 521 here. Now this mutable borrow is dropped. Mutable really doesn't sound like a word. This mutable borrow is dropped, and we can now create an immutable borrow of point, and we can see that data has in fact changed, even though this is maybe an immutable point. Okay. This is the last example I'll go over. The last one covers this concept of partial borrows, but I don't necessarily think it's important to cover, and so we won't. If y'all do end up, running into this issue, you'll find plenty of documentation for it online. Okay. Apologies for saying the words mutable and borrow and immutable about 100,000 times during this lesson. But I hope that this was helpful. Let me know if you liked this sort of structure. I think I took it maybe a little bit too slow, especially in the early examples, but hopefully just going through these examples can help y'all when it comes to actually doing this on your homeworks and doing this in your MPs. So if you have any questions, make sure to let us know. Best of luck on your MP, and have a wonderful week. Thank you.